above the maximum frequency we like to capture. The maximum frequency we'd like to capture is 20 kilohertz. So we make it more than double. For whatever reason, 44.1 is what they settled on, and that's what we've got. That is like the minimum I'd ever like to listen to. Any more than that, I'd really rather not listen to it, because we can't capture that full range.
And so if a song is basically like all bass, you could maybe take the sampling rate down to like 20 or something, 20K or something, right?
Yeah, sure, maybe. If you didn't want to capture anything over 5,000 kilohertz, you absolutely could, and it wouldn't be destructive. But presumably you want the whole range. And this usually will go up to as high as into like almost 400 kilohertz I've seen. But usually the nice frequencies are 44.1, and then 192 is the next one.
They lost you again.
Again? God damn it!
Oh.
Alright,
Error 21.
I might just use Chrome.
Yeah,
It's
check
scripted.
that.
I might just switch to Chrome.
Is it just like Wi-Fi or is it like gym?
I don't know, I'm switching to Chrome.
Code shit, game shit.
I mean, if I had to guess, I would say RPI Wi-Fi, because fuck RPI Wi-Fi.
Same.
Yeah. Oh well.
It's pretty awful.
When in doubt, use Google products. We are.
We'll use Google products together.
Hey,
Yeah,
Jim.
that's what I mean.
Remember, Jim?
Alright, where did you guys see me leave off? Hello, nerds? Rocco?
We just dropped 36 seconds ago, like it wasn't that bad.
Okay, okay.
Yeah. It was, yes, perfect.
You went from the NILAC folder back to the PCM sampling, right? Slide.
Correct. We went back one.
And then we lost you, like, basically, when as soon as you hit the sampling.
Okay, well, Rocco, do me a favor and disable your video, just so that we have less load on the Hangout. Because Google, alright. So I'm gonna jump back into it. We pretty much covered all this, and what you guys might have missed is that we need twice our sampling rate must be twice the maximum frequency that we'd like to capture, because otherwise we can't approximate the waveform correctly. Fold over shows that we can always assume it's under half, and therefore we will have only one wave that we can approximate to. Moving on. So the next parameter is bit depth. Bit depth, we want higher is better. And here's the two common bit depths that PCM uses. It's either 16-bit, that's what you usually get. So the most common format for audio in PCM encoding is 16-bit with 484.1 hertz, or kilohertz sampling rate. So 16 by 44.1 is how it's abbreviated. And the best one that you'll see commonly used is 24 by 192 kilohertz. That's like if you can get 24 by 192, that's some good audio. There's higher, but that's like, you know, after that it's kind of like, what are you doing? And some of the features of this is when you add these extra bits, it actually doesn't add accuracy, it adds the ability to go higher and lower. So you actually don't gain a better fit on the wave after the 16 bits, they actually just use it to go more. So you end up with the ability to go quieter and louder, essentially, on your wave. So you gain, what is this, 48 extra decibels of range. So most music fits within that 96 decibels of range, not a problem, but the 144 is for like when you have an orchestral piece that has points where it's extremely quiet and points where everything is playing at the same time. Someone writes the music specifically so that they're going to use all of that range. They need to have a bit depth of 24 bits, otherwise you're not going to hear all of it.
It's almost like resolution in a way.
Yeah, absolutely. Yeah, it's dynamic range resolution, like your ability to capture the entire range of quietest to loudest, versus like sampling rate, which is frequency.
Quick question.
Yep.
So when someone markets like AFLAC or whatever, ALAC, I guess, like the lossless audio format, it can't be really truly lossless. I guess it's just at whatever the studio was sampling at. Like, what does that actually mean? What does lossless mean as far as digital compression happens?
Sure, so I purposely kind of stayed away from compression because it's a little bit different from this topic. But to answer your question, it means that you're not losing any information from the audio that was recorded. So essentially, when you have a FLAC, when you have a lossless piece of audio file, you get everything over 16 kilohertz is still intact. You have no compression, you lose no information. However, when you compress a file, you actually take out the pieces you don't think people can hear from the file. You literally take out those sounds from the file until the file meets a specific size or fits within a specific dimension as far as like bit depth or sampling rate. So you might remove sampling rate, you might shrink your bit depth, but mostly it's taking out sounds at certain frequencies right after really loud things. So it will take out the quiet things right after really loud things because it doesn't think you can hear them. Or if a loud and a quiet thing are going to happen at the same time, it will take out the quiet thing and therefore be able to represent it in less bits. So it might, can you guys see my cursor? Assuming you can see my cursor, you would be able to take out any sound that would go up here and just keep 16-bit depth. You would be able to take out a sound that gets played right here, really low, right after this high volume sound plays. You'd be able to take it out, and therefore you could use no bits to represent that space because it would be quiet. Interesting techniques. It completely relies on what people are able to hear, in big air quotes, and like the psych of audio and listening. Yeah, so that's compression in a explain like I'm 5 as best I can. Okay, any other questions before we move on? Good. So DSD is our other format that is often used to transmit this kind of audio to your DAC and store it as well. So it's not really used very much. It's proprietary to, I believe, Philips and Sony have a shared patent on it. And it's not really used for mixing either because it's really hard to apply different filters to this. You kind of convert it back to the PCM and then go back again. You can see I'm reusing the picture just because it's really nice. Essentially, we're going to talk more about how this actually works later on. And we're going to talk about the conversion from that file format and how it relates to DACs and amplifiers that leverage the technology. But essentially what you need to know is instead of using a wave that goes up and down, it turns it on and off and it adjusts how wide each pulse is to represent the wave. It does that using math, and we're going to talk about it when we go to talk specifically about pulse width modulation. I believe I covered all this. Okay, so just context switch a little bit. Now we're going to talk about some electronics. We're going to talk about how a multi-bit DAC takes a digital signal, specifically this is usually a PCM signal, so it's a bunch of bits that can directly be converted into an analog wave. So when you get DSD to one of these DACs, usually it is converted to PCM and then put through this, instead of trying to use a DSD format into this. This is interesting because there's another DAC that will do the opposite. But this DAC is rarer, and it's rarer because you have to match these resistors perfectly, otherwise it won't work. So I guess that will make more sense if I explain how this works. So you have your current going from here to here, right? This is where it's going to flow outwards, and you're going to have these bits, so this is a 3-bit DAC, and you have B1, B2, B3. As you turn these on, the voltage will flow from the bit, from what represents the bit, down into here and out your outwards output, whatever you want to call that. I'm not an electrical engineer. Essentially, because this resistor here is exactly 2R, and this resistor here is these add up to 2R, you're able to actually take this bit, send it out here, and because it's behind all of these other bits with all these other resistors, at this line, the resistance here is still R, which means this is again 2R, because the resistance before here is R. It adds up using math and PE stuff. Charlie explained it to me once before, but basically these add to 2R. This is like 2R over 2R plus 2R. Am I making any sense? Essentially, what the main thing you have to understand here is bit 1 is 1/8, I believe 1/4 or 1/8 of its current is actually applied to the output. B2 is going to be 2 times that, and B3 will be 2 times B2. So think of this as powers of 2 applying each bit individually from the PCM encoding into an analog signal. So essentially, because the voltage from B1 is behind all these other resistors, it will only apply, let's say I think it's 1/4, and this is 1/2, and this voltage is applied. Okay, so this B3 applies half its voltage, right? Charlie can double check me on this. I'm pretty sure B3 applies half its voltage, B2 applies 1/4, and B1 applies 1/8. And the whole point of this is that you can use those bits to literally directly input your sound from your PCM directly into an analog signal without having to do any crazy approximation. You don't have to guess, you don't have to do any math. You just put the voltage there, you turn the bits on when they're supposed to be on, and you turn them off when they're supposed to be off. You change the signal as fast as your sampling rate. So if your sampling rate is 44.1 kilohertz, you will change this every time you take a sample. You're changing these bits to be the newest approximation, and then it will change the waveform and create that nice sine wave that we're looking for. Does that kind of make sense so far? Please ask questions, because I know this is a little bit complicated.
So what are those 3 bits then? Are those inputs from the digital side? I thought the input is the bottom left.
So that's ground. This is the ground, and the current will flow this way. Like the output is here.
So this is for DSM.
No. Okay, we context switch.
Wait.
Okay, this is a digital file format. Okay?
Okay.
PCM and DSD are digital file formats.
Okay.
R2R multibit is a DAC type. This is a type of converter to go from a digital to an analog signal.
So literally, what happened to it?
You take the PCM file and you match the bits